Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. So, today we are actually going to be continuing into acids and bases. Now, y'all already did start this unit a little bit when we had y'all review some of the previous concepts over acids and bases, stuff that y'all probably learned in your previous chemistry course. So, make sure that you have gone over it, you've reviewed those, you've done that practice, but that was something that you should have done last week. All right. Now, we're going to go ahead and continue on in our acids and bases, and we're going to start with today's lesson, which is going to be over acids. And this is actually going to be a multi-day lesson in terms of acids. So, part one, day one of acids. So first off, when we are talking about acids, one thing to recognize is that most acids that we deal with in chemistry are going to be what we call oxyacids. And what that means is they're acids that have an oxygen in them. So they've got an acidic proton that is attached to an oxygen. Now, some examples of an oxyadded would be like sulfuric acid or nitric acid or hypochlorous acid or phosphoric acid or all of those things, any of those acids that have that polyatomic ion attached to them that has the oxygen as a part of it, that is going to be what we call an oxyacid. Now, we do need to recognize the difference between a strong and a weak acid. Now, here are some examples of some weak oxyacids. So I have phosphoric acid, I have nitrous acid, and I have hypochlorous acid. Now, those are all weak. How do I know that? Well, remember, we know that it's easier to just memorize our strong acids than it is to try to figure out what would be the strong versus the weak acids. And so, as a reminder, your strong acids are going to include a sulfate ion. Sorry, I'm just going to zoom in here. Sulfate, nitrate, chlorate, perchlorate, and then a bromine, iodine, and chlorine ions. And the way that I have always remembered those are so, no, clo, brickle. And that's always helped me to remember my strong acids. And again, being an acid, what we typically see is that they are going to start with that hydrogen. Now, we might have more than one hydrogen there, right? With the sulfate there, we would have two hydrogens. But this would be our list of strong acids. So if it doesn't fall into one of those 7 acids, then it is going to be classified as a weak acid. Okay? Now, when we are talking about acids, one thing that we can do is, if we're within a series, is we can determine the strength of the acid based off of the number of oxygen atoms that we have. For example, if I have perchloric acid, HClO4, it is going to be stronger than chloric acid, and that's going to be stronger than chlorous acid, and that's going to be stronger than hypochlorous acid, right? And so as we're moving down, as we're decreasing our number of oxygens, we are going to see a decrease in that strength of the acids. Okay, so H2SO4 would be stronger than H2SO3, which would be stronger than H2SO2, and so on, right? Now, electronegativity of the oxygen does draw those electrons away from that oxygen to hydrogen bond, which is why the more oxygens we have, the stronger the acid would be. Okay. Now, acid strength is going to increase with increasing electronegativity as well. So not only do we have to think about, okay, well, if I've got different numbers of oxygens, but I also need to think about, okay, well, what is that other element that's bonded there? So if I were to compare this hypochlorous acid to this hypobromous acid to this hyperiodous and so on, right? If I were to compare those, what I would need to do is then look at my electronegativity. And so I know that chlorine has a higher electronegativity than bromine and so on. Okay, and so we would actually base their acidic strength based off of their electronegativity after we have looked at those oxygens as well. So if we're looking at the same number of oxygens, then that would be what we would do to compare their strengths. Okay, now one thing to note is that if I've got an organic acid, so we just talked about our oxyacids, right? So if I've got an organic acid, they are usually going to be weak acids. Now, what makes them organic is that they are going to have what we call a carboxyl group. And so a carboxyl group would be, okay, I've got the rest of it, right? And then that's going to be attached to a carboxyl group, which is going to look like this. So this right here is my carboxyl group, all right? Now, this could also be written as that. Okay, again, they look very similar. They're basically the same thing, right? We're just now showing that bond between that oxygen and that hydrogen. If I look at something like acetic acid here, acetic acid, this would be my carboxyl group. So if I were to actually write out my Lewis dot diagram for this, I would have my carbon bonded to the 3 hydrogens, and this would represent that R that I was showing you here with this carboxyl group, okay? And then it's going to attach to my actual carboxyl group. So carbon with the double bond of that oxygen, and then that comes down to my hydroxide there. Okay, and so this would be acetic acid's actual Lewis diagram. But one thing that I do want y'all to be able to recognize is that carboxyl group that is attached, because we do need to recognize if something is an organic acid. Okay. All right, so that would be your organic acids. So now let's look at what we call a hydrohalic acid. So a hydrohalic acid is going to be anytime we've got that hydrogen attached to a halogen. So if I'm talking about fluorine, chlorine, bromine, iodine, those are all going to be halogens, right? And so they would all be classified as hydrohalic acids. Now, there is one hydrohalic acid that is classified as a weak acid, and that is actually going to be HF. Now, here's something to wonder why. Well, remember we talked about earlier, your increasing electronegativity tends to mean that you're going to be a stronger acid. Well, yes, that is true. However, fluorine actually has such a high electronegativity that it has a very, very strong attraction to that hydrogen. And so as a result, we actually do not see that dissociation occur to its completeness, because there is such a strong attraction between that hydrogen and that fluorine. So, and that's what this next sentence is saying, is although the hydrogen-fluorine bond is a very polar bond, that bond is essentially too strong. And so we do not see it completely dissociate, which is going to be kind of one of those defining characteristics of a strong acid. Okay. Now, when we are looking at weak acids, their strength is compared by their Ka value, all right? And so the smaller the Ka, the weaker the acid. And so what we're going to be doing is we're going to be using that equilibrium to solve for those different, the strengths of those acids, all right? And so we'll actually learn about that next class. Now, another thing to note is that if we're talking about a strong acid, we don't talk about the Ka value. Why? Because it is going to have such a small concentration that it's not going to be measured accurately, right? And so a lot of times we talk about things being negligible. That's kind of in the same vein as this, and that we don't need to worry about it just because it has such a very small effect, okay? Now, next thing, amphoteric. An amphoteric substance is a substance that can act as an acid or a base. There are a few things out there that can act as an acid or a base. Water is one of the biggest ones that we see that happen in, because water has that hydrogen that it could be a proton donor, proton acceptor, right? We talk about how those electrons are transferring, and we know that water can act as that acid or that base. Water also goes through what we call autoionization. And so basically what that means is you take your water and it can act as, again, an acid and a base. And so what we see here is that here we've got our base and our conjugate acid. What happened? Well, one of these gave away a hydrogen to the other, and so it became this hydroxide. So this acid became that base, that conjugate base there, and then this base turned into this conjugate acid, right? And so what we see is that, bases tend to be proton acceptors, acids tend to be those proton donors. And so water will automatically do this. Now, this is happening all the time, even in just like tap water. We do have this auto-ionization that is constantly occurring. But because you've got that equal amounts of acids and bases, water's pH would end up being 7, right? Now, the ion product constant of water, which is your Kw. Your Kw is going to equal the concentrations of hydronium and hydroxide, or we can better classify that as the concentration of hydrogen and the concentration of hydroxide. So we take those two and we multiply them together, and we do end up with our Kw. Now, if we're talking about water and we're talking about it at 25 degrees Celsius, the Kw is going to equal 1 times 10 to the negative 14, because that means your hydrogen and your hydroxide concentrations are going to be equal to one another. And so your hydrogen concentration equals your hydroxide concentration, and that number is 1 times 10 to the negative 7. And so when we multiply those two together, we would end up with 1 times 10 to the negative 14. All right. Again, no matter what an aqueous solution contains at 25 degrees Celsius, its hydrogen and hydroxide concentrations are going to equal 1 times 10 to the negative 14. And so this is why when we talk about pH, we talk about how it will go up to a scale of 14, right? 1 to 14. We know that if we've got a neutral solution, our hydrogen concentration equals our hydroxide concentration. If it's acidic, you've got more hydrogen concentration. If it's basic, you've got less hydrogen concentration. But this is all going to be at 25 degrees Celsius. And so if we change our temperature, we could actually see changes in those as well. All right. Another thing to know is that if we're talking about pH, to solve for pH, we're going to use the negative log of our hydrogen concentration. And so if our hydrogen concentration is 1 times 10 to the negative 7, then we would solve for our pH by plugging that number in, and we would find that our pH equals 7. Okay, so one thing that I do want to point out is that if we are looking at this, if we've got a 1.0 times 10 to the negative 7, if your mantissa, which again is those numbers in front of the x, is 1, then we can just take this exponent, this characteristic, and it's going to equal our pH. Okay, and so that's just kind of a math trick for you to kind of help you out if you need to take a shortcut in terms of time. Okay, next thing we have is sig figs in pH. Yes, pH, with our acids and bases, we do actually have a separate set of rules that we follow for this. Now, how do we do this? Basically, what we do is the number of decimal places in the log value should equal the number of significant digits in the original number, okay? So the number of decimal places in the log value should equal the number of digits in the original number. So let me give you an example of that. Let's say I've got a pH of 7.395, okay? So to solve for my concentrations, then what I would do is I would do this pH to the power of negative 7.395. And what that would give me would be 4.02717 times 10 to the negative 8. Now, that is not my final answer because I do need to take into account my significant digits. Now, if you remember, it is the number of decimal places in my log value. So the number of decimal places in my log value. So here, this pH is my log value. So how many decimal places do I have? 1, 2, 3 decimal places there. And so my answer here needs to make sure that it does have 3 significant digits. So 1, 2, 3. So my answer should be 4.03 times 10 to the negative 8 in terms of that hydrogen concentration. Okay, this would end up being my answer. Okay, and so when we're looking at this, those significant digits are very, very important, especially in acids and bases, because just a small change could affect our pH, which then would ultimately change some of our values. All right. Now, one thing to take note of is that pH and pOH are what we call logarithmic functions. And pH stands for changes by 1 for every power of 10 change. And so it is going to be a big factor in terms of how we're actually going to be changing those things. And so a pH of 1 versus a pH of 2, we've got 10 times the difference there. Okay. So pH decreases as our hydrogen concentration increases. Okay, now pH plus pOH, so if we're comparing the power of hydrogen versus the power of hydroxide, what we would find is that if we add them together, they're always going to add up to 14. Now, to solve for that, again, I've already talked about this. If you've got your hydrogen concentration, it's going to equal the antilog of the negative pH, or hydrogen concentration. So 10 to the negative pH would be how I'd solve for that. For hydroxide, it would be the same thing, but again, make sure that things are matching up. So if I've got hydroxide, I would use my power of hydroxide there. All right, we do need to keep those in mind because I cannot make a direct conversion from our hydrogen concentration to a hydroxide. I cannot do that. Okay, and so do keep that in mind when you're solving these pH problems and these concentration problems, because that can be a big factor that a lot of students make mistakes on. Okay, all right. Very last thing that we've got here in this set of notes today is calculating the pH of a strong acid solution. So when we calculate the pH of a strong acid, it is generally very, very simple. The pH is simply calculated by taking the negative logarithm of the concentration for a monoprotic acid. Now, this is actually very important. Monoprotic just means you've got one hydrogen there to work with, one of that proton to work with. So, for example, if I've got the pH of 0.1 molar HCl, again, this is monoprotic. Why? Because there's only one hydrogen, and that is going to equal 1. Okay? Now, if the concentration is less than 1.0 times 10 to the negative 7, the water does become an important source of that hydrogen concentration, and the pH does end up turning out to be 7. Now, the pH of an acidic solution cannot be greater than 7 at 25 degrees Celsius. Why? We know because pH, if it is less than 7, it is going to be acidic. If it is greater than 7, it is going to be basic. All right? Now, another thing to note is that when we're calculating the pH of something like H2SO4, one thing to note is that it is not monoprotic. We do know that sulfuric acid is a strong acid, but it is not monoprotic. And so solutions, if it is more dilute than 1 molar, at that concentration, the hydrogen of the HSO4 minus must also be calculated. And by that, I mean, remember when we have acids in a solution, when they dissociate, they lose 1 hydrogen at a time. And so we start off, and it would be exactly what you think, where you do the negative log of that hydrogen concentration, that'd be your answer. However, it does not take into account that HSO4 minus, because there is still 1 proton to remove. And so we have to take into account both of those. And again, we'll teach you how to do that. Now, before we actually move on, let's just kind of focus on some monoprotics here. So it says calculate the hydrogen concentration and pH in a 1 molar solution of HCl. Well, first off, my hydrogen concentration is going to be equal to 1. Why? Well, because this is my source of hydrogen. It is in a 1-to-1 ratio there. And so since there is 1 HCl for every 1 hydrogen, that would be the same concentration. Okay? So then to solve for my pH, I'm going to take the negative log of my hydrogen concentration. And so I would find that my pH is going to equal 0. Okay? And so very, very low, so it would be a very strong acid, right? Okay, so I want y'all to go ahead and solve this last problem here. After that, we're going to go over it, and then we will be done with this lesson. All right? So pause your video, solve the problem, we'll go over it. All right, so this is what you should have ended up with. You should have found that your pH was equal to 10. Now, as a reminder, since this does start with that mantissa as being a 1.0, we know that if we're solving for pH, we can just take our number up here and it turns into our power down there. All right, y'all, that is it for this set of notes. As always, let us know if you have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.